have to do is evaluate this over a closed surface of the Maxwell stress tensor to the Dn. So now let's consider the example. All right, now here we have just a chart, right? Chart that's not moving. So we expect only an electric field produced by this chart configuration. You don't have a magnetic field. So in that case, then the Maxwell stress tensor, since B is equals to 0, the Maxwell stress tensor becomes just only the electric field, which is given by this. So just only the first term. So this becomes epsilon naught of Ex 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 that's X hat Ex Ey Y hat Ex Ez Z hat Ex E of Y X hat Ex or we can put it Ey Ex, doesn't matter. So then you have Ey Ey Y hat Ez no Ey Ez Z hat, and the third row is going to be E X Ez X hat E Z E Y Y hat, and Ez Z hat, plus the diagonal matrix, which is given by that. So plus half of E squared 0 0 0 half of E squared Y hat is X hat 0 and 0 0 half of E squared Z hat. So we have to find the elements of this matrix to find the force.
Dr. Liu, it has a minus sign on the...
Yes, yes, thank you. And epsilon is for force, so I have to. So how do we find these elements? And what kind of surface I should consider to find this force? So I'm interested in the force exerted on the upper, on the northern hemisphere of the sphere, right? So what kind of surface would you recommend? So I'm interested only on the force, although we have a solid sphere. So the charge is over a solid sphere, okay? But I'm interested only on the force on the upper hemisphere. So I must consider a surface that encloses just only this upper part of the sphere. So you have to, the surface that you want to consider, it should be the surface that encloses the charge over which you want to find the force exerted. So I consider this kind of surface, and I must know the electric field on this surface if I want to evaluate this. So for the upper surface, all I need to know is the electric field on this surface. All right? So you can divide the surface into two. the curved one and the plain circular surface. So for this one, it's easy, you can express the electric field. But for the bottom plane, you have to know the electric field inside the sphere, because you are considering, points all over this plane. But on this one, you consider only points on the surface. So what's going to be the electric field? So first, find the electric field. Find the electric field E. So that's going to be E equals to what? If I use spherical coordinates, this is going to be for R equals to capital R on the surface of the sphere. How can I explain that? It's just the electric field of a solid sphere, right? So that's going to be Q over 4 pi epsilon naught 1 over R. And what should be the direction? Unit vector R. So that is on the surface. That's what I need to evaluate this integral for this surface. Okay? Yes?
Should it be R squared?
Yes, R squared. Yeah. Thank you. And but on the plane, because I have to integrate it over this plane, and over this plane, the electric field changes as you go from the center outward. So you need to know, in general, the electric field at some distance r less than capital R inside the solid sphere. So how do we express that? So just to make it short, that is given by Q over 4 pi epsilon naught of that if I apply Gauss law, that's going to be Q enclosed over 1 over R squared, right? Just a simple Gauss law along the unit vector R. That is for R less than capital R. But how can you relate Q enclosed for a uniformly distributed? So where Q enclosed is going to be just the total charge over R cubed over R cubed. You can show this one, right? So now, I got the electric field in spherical coordinates, but when you deal with Maxwell's stress tensor, the electric field must be expressed in Cartesian coordinates, because the elements are expressed in terms of Cartesian coordinates. So I must express these in Cartesian coordinates. So how can I do that? So in Cartesian coordinates, all I have to do is to express the unit vector in terms of the polar coordinates along x, y, z. So how can I express r hat? R hat is a unit vector along the radial direction, which is given by partial derivative of r with respect to r, where r is expressed in spherical coordinates divided by magnitude of r with respect to r. So that would give you what? Sine of theta cosine of phi along x hat plus sine of theta sine of phi along y hat and plus cosine of theta along the hat. So now first let's find the electric field at r equals to capital R. So that is going to be this times by this, and that would give you for the x, y component of the electric